Okay, so the question is the usual theta of n square implementation of insertion sort. uh, to sort an array uses linear search to identify the position where an element is to be inserted into the already sorted part of the array. If instead we use binary search to identify the position, the worst case running time will be, and then we have to choose the correct choice. So what this guy is saying is, suppose you have this array, okay, and what you have to do, you have to do insertion sort to sort the elements. And he's talking about the usual implementation. Okay, so what you have in the usual implementation is, to the left you always have a sorted array, and then you pick your element and you insert it into the sorted array at the correct position. Okay, so what you do, you start with this one, so you start with the first element. This is always sorted. Okay, this is what you do in the usual implementation, and then you pick this one and then you put it at the right position. Then what you will have, you will have two elements that will be sorted. Okay, and then you will pick the third one and put it in the right position. That's what you do with the usual implementation. But now what it is saying that, okay, and in the usual implementation what you do is you do linear search. Okay, so suppose you have a sorted array up till, let's say, these I elements in the beginning are sorted, and you are picking up this element I plus 1th element, and you have to place this element at the right position in this already sorted array, so that next you have a bigger sorted array and you can go to the next element and so on. Okay, so how do you find the right position for this element to be put in this sorted array? What you do usually is the linear search. You compare this with the element here, and okay, if this one is smaller than this one, then you swap them. Okay, and then you go ahead and compare, and you keep on doing this until it finds it right position, and which gives you the theta n square implementation. Okay, so what this is saying is that since you already have a sorted array out here, okay, so this part is already sorted up till here, so instead if you use binary search to identify the position, because you know that binary search just takes log 2 base uh, n time for n elements. That's what you know about binary search. Alright, so if you can search this part with using this binary, you will be done in log 2 n time, and then you can insert it in the right position. So what will it do? Will it improve the time? So will it make it theta n log n, improve it from theta n square, or you know, or will it be still theta n square? So that's the question. So it might appear in the beginning that, oh wow, this is binary search and we can really do it fast, but it turns out that you cannot do it better than that. And the reason for that is that, suppose you find your element using binary search, so suppose your position using binary search, so suppose you have to insert this I plus 1th element in this sorted array, and so how much time will it take for the binary search? So you can say that the time it takes is log base 2 I for out here. Okay, and you have found your position. Okay, then what? Then you have to insert it there, but before inserting it there you have to shift all these elements. Okay, suppose you have to insert it at this position. Okay, then what you need to do is you need to shift all these elements to the right and then insert it there. Right, that's what you have to do. So that shifting gives you some extra cost in, and that's where it remains the same, as you will see. So what it is talking about is the worst case. So in the worst case you might have to shift all the elements to the right and then insert your element in the beginning right here. So I plus 1th element goes here and these I elements are shifted to the right. So in that case the number of operations are, these are the operations for binary search, and then you have to shift I elements. So for this I plus 1th position you have to do these many operations. Okay, and for your insertion sort you keep it doing from you keep this whole thing doing, okay, from I is equal to 1 to the last element, nth element, okay. And if you sum this up, what will you get? This thing will be log 2 1 plus log 2 2 and so on. So you have so many additions in log, which gives you their product, basically 1 into 2 into 3 up till n, plus, and this is nothing but summation of first n terms, okay, which has a formula which you know, that n into n plus 1 by 2, okay. If you add the first n terms 1 plus 2 up till n, you get this thing. And so if you write it, and this thing, what about this thing? This thing is in O of n log n, okay. This is the standard result, because this thing is what? How is it in O of n log n? Because this thing is log to n factorial, basically, and this thing is definitely in O of n log n. And this part, what about this part? This is in O of n square, okay. So in total you are still in O of n square, okay. So you haven't done better than that, and it's simpler to see that it's in, it still remains in n square. That's the idea behind this.